Hello guys, welcome back. Hope you are doing well and learning a lot from the current series in which we are learning the ANSYS CFX. In today's tutorial, we are going to see how to conduct a non-Newtonian fluid flow in an annulus. Basically, the annulus is the area between two circles that you can see is marked here as gray. So the area you are seeing in the gray color is the annulus. That is trapped, you can say, between two cylinders. So let's start. First of all, we will talk about the problem, like what we have to solve by using the ANSYS CFX. So in this problem, we have to conduct a simulation in which the inner cylinder is rotating at 31.33 rpm and the rotational axis is z, and the fluid is non-Newtonian. So we will use Ostwald-de Vallée model, and these are the fluid properties. So what we will learn today, we will learn how to set up rotational boundary condition, how to set up a non-Newtonian fluid in the ANSYS CFX, how to conduct a free surface flow in ANSYS CFX, how to conduct a transition simulation as we have already done it with it. Also, we will see some other expression we use while doing the simulation. So let's start. First of all, drag and drop the ANSYS CFX system. We have to import the meshing. I will add the source file in the description. Okay, the mesh is imported. Now come to the setup. Okay, delete the default domain. Come to the material section. We have to define a new material. Thermodynamic state is liquid. Okay, if we come to the material properties, the density is 10,000, molar mass is 1 kilogram, and then we have to come to the transport properties, expand, and we have to provide the dynamic viscosity. The value is basically the non-Newtonian. So we are we are going to use the mathematical model of Ostwald-de Vallée. So we have selected it. So come to this document and see the properties. So the property is 10. Okay. Paste it. Now see the strain rate. And maximum is 100. Power index and time constant. Power index is 1.5. Okay, all the values are fine. I have done a mistake in the document. So the minimum shear stress rate is also fine. Okay. Okay, we have defined the material. Click on OK. So now we have to define our domain. Choose the location, and the material is non-Newtonian. Also come to the fluid model, turn off the energy model. This is laminar flow, and okay, that's fine. Now provide the boundary condition. Select the rotating wall. This one, come to boundary details, wall velocity. It is rotating wall, so click on this. So provide the revolution per minute, which is 33. 1 second. Yeah, it is 31.33. 31.33 revolution per minute. Okay. Click on OK. So now come to the boundary. Also, we have to define the symmetry. Side 1, symmetry plane 1. Okay. Now come to boundary condition again. Side 2, symmetry boundary condition for plane 2. Click on OK. All done. Now come to the solver control. High resolution is fine. Time scale factor is also fine. Change the target result to 6. Okay. So okay, all done from here. Now come to the output control. We have to take some of the other variables too. Standard is fine for it. Close this window. Come to solution tab. Click on double precision. The 6 are fine because it is not a large problem. Start run. Okay, the simulation is completed within seconds. Create a contour. Click any of the side so we can see the pressure. Let me increase the number of contours to 50. So now you can see the difference in pressure. Also, if we see the velocity, you can see the velocity is high near the cylinder. Also, I can instead of constant color, so you can see because the wall has a constant velocity, you can see the pressure on the wall too. Okay, now we have to create a plane. Click on plane. Okay, create at the center. Change the plane type to sample. Now it's fine. 32. Theta sample 24. And change the radius to 0.3. Click on apply. You can see the plane is being created. It's even outside the domain. That's not a big problem. Come to the render. Hide the face and show contour lines. You choose the color, like I want to see this in blue color. Click OK. Okay, so now you can see the plane. Now basically we have created this plane to see the field vector. So come to this vector plot. Click OK. Select the plane. Click on apply. So hide this plane. So now you can see if I increase the symbol size to 3, so now you can see how the fluid is being rotated in this annulus, the direction and the velocity. Also I can, sorry, we have to decrease it, maximum number of points to 250. So these are the maximum number of points. Instead of vertex, equally spaced if we get. So now the more clear picture is presented. Now let's come to plane again. Insert a contour, plane 1. So we can see that we have only a small number of variables here. To show more, click on this window, these 3 dots, and we can see the other variables too. I want to see the dynamic viscosity because the viscosity is a variable in our case. So I want to see this. Click on OK, apply. So you can see how the velocity is changing. Sorry, viscosity is. Change the contour to 50. So you can see the viscosity is high near the wall, rotating wall, and it's low uh, farther away from the cylindrical wall. So why? What is the property? This is the property of basically non-Newtonian fluid that we want to study here. That with the like when the rotation or the motion, or you can say basically when as much as the force will be increased that is being applied on the Newtonian non-Newtonian fluid, the viscosity become higher. The most generic example of non-Newtonian fluid is blood, or you can say the custard, toothpaste. These are some of the example of non-Newtonian fluid that behaves like a fluid and a solid too. And all of the viscosity depends upon the basically depends upon the shear stress. So now let's come to the strain rate. Again, click these three dots. You can see the shear strain rate here. Click OK, and you can see the strain rate. Okay, all done with the simple simulation. Now come to the workbench again, duplicate, open the setup, come to analysis type, transient, total second are 5. I want to run it with 0.01. Click OK. Come to output control, create the results. Okay, select standard, interval is 1. Click OK. Close this window. This window too. Open the solution here. Double precision, initial conditions, but we did not provide the initial conditions, so the error will come. So again, open the setup. Come to domain initialization. Click OK. All the errors are resolved. Now again come to solution. Okay, start run. Okay, the simulation is completed. We click on OK. Now come to the results. So if I plot the vectors, so now you can see how the flow will develop. Velocity, so we can see the eddy viscosity. Click on these three dots. Sorry, dynamic viscosity. Click apply. So you can see at the start the velocity is very low, but the time the velocity the viscosity increases due to the shear strain. Please do not miss any of the video in this series. There are lots of things that you can also implement in your other simulation. Like I've just told you about the angular flow, or sorry, angular rotation. But you can also like implement this thing into the non-Newtonian fluid, or many of the other, you can say the, like, if you want to do the simulation of a mixing tank, you can implement this idea there. So okay, now we will also see the shear strain. Simulation in which we are going to use the multiphase. Like now I want that the half of this annulus area will be filled with the non-Newtonian fluid and other half will be air. So we will see how the non-Newtonian fluid act with the air in a rotational zone. So let's come to the setup. So what we want to do, we want to add a restriction that if the y, basically in the y, if we take the y direction, if the y is lesser than 0, let me also show you the coordinate from point so you can have a better idea that. So this is our coordinate system. So if you see up to this line here, there is the non-Newtonian fluid, and above there is only air. So to do that, we have to make an expression. We will use the if function. So I will say if y is lesser than 0, I am taking the unit of meter because anyway, any of the units you can use in this case because the value is 0. So the non-Newtonian fluid ratio will be 1. If the y is greater than 0, the value will be 0. Apply. Now create another expression and just 1 minus expression 1. So remaining area will be filled with the air. So now come to this domain and define a new material. So it's automatically taken the value. Also now I want to enable the gravity. So 0, 0. The reference density I will take 1.25, and the gravity is acting in the negative direction of y. Okay. Now come to the fluid models. It's free surface model. Come to this tab. Okay. For volume fraction, I will use the expression. Okay. Click OK. Now again come to the output control. In the result section, I want to make it 10 and standard. Click OK. Also in the rotation, I want to decrease this rotation to 5 revolution per minute, or you can say 6. Okay. So all done. Also the analysis type, I want to make it 1 and have to decrease it to 0.001 because now it's also include the free surface motion. And in the solver control, decrease the RMS to 4. Also in output control, it will take lesser time if I make it 25. Click on OK. Also okay, all fine. Here, close this window. Again come to the solution. double precision, run processor, initial conditions, start run.